Howdy folks, today we're going to be talking about naming compounds and so we're only going to be focused on one type of naming compound, that is an ionic compound. And so first thing we're going to do is we're going to define what an ionic compound is. And an ionic compound is composed of a metal and a non-metal. Now in these compounds, the metal is going to be transferring its electron to the non-metal. Now when it does this, the metal itself is going to become positive charge, and we call that a cation. And the non-metal will possess a negative charge because it's accepting the electron, and electrons are negatively charged, is going to be known as an anion. Now before we can do anything, what we need to do first is look at the periodic table and understand where the metals are found and where the non-metals are found. And so we're going to be looking at this specific one here. Now what I want you to do is I want you to focus on the black staircase found here. And what we want to do is we want to understand is what's the importance of that staircase. And that is the importance of that staircase is to separate the metals from the non-metals. Now if you go to the left of the staircase, this is where you're going to find your metals, which I'm abbreviating as M. And if you're to the right of the staircase, this is where you find your non-metals. Now there are a few elements that are on the staircase that are touching it that are considered metalloids, but we're not focused on that at this particular moment. So what we are focused on is, where the metals are found at and where the non-metals are found at. Now we're going to be looking at the various groups on the periodic table. We're going to go from left to right, and so what we want to do is we want to focus on 1A, group 1A, which is all the way on the left hand side of the periodic table. Group 1A is called the alkali metals, and group 1A has a +1 charge. Group 2A is known as the alkaline earth metals, and it has a +2 charge. This whole middle group that you see me highlighting here is called the transition metals, and the transition metals have a varying charge, and we're going to talk about transition metals a little bit later. We get over to group 3A. Group 3A is called the boron family and has a charge of +3. 4A is the carbon family and has a charge of ±4. And what's important about this is the reason why is we have two non-metals and we have metals found below. So we have both metals and non-metals. That's one reason why it has ±4. Now once we get to the pnictides, which is in group 5A, pnictides is spelled P-N-I-C-T-I-D-E-S, just for that spelling, has a -3 charge. Group 6A, the chalcogens, has a -2 charge, and the halogens in 7A has a -1, and then last but not least, the noble gas have a 0 charge, as they don't really go through any type of reaction. Now what we also want to do is we want to understand as to the importance of why we want to learn the charges of these different elements, and that is because when we start to write formulas and names from those formulas, we want to make sure we understand what the charges are, because each of these compounds possess their own ratios for each element. Now I drew what is called a mountain, and I want to just show you this because sometimes it's easy to remember this mountain and it helps you to understand the charges. Now this is going left to right across the periodic table. The first group that you come to is 1A, it's +1. 2A is +2. 3A is +3. 4A is ±4. You're at the top of the mountain. You can either go up or you can go down. Now once we start to go down, we're going to be at 5A, which is -3. We're going to be at 6A, which is -2, 7A, -1, and then the 8A group is 0. So this mountain is just to help in remembering the charges of the different groups that you find on the periodic table. And remember, the transition metals are not included here for the reason that they vary in charge. Again, we'll talk about that later in this video. So we can break up ionic compounds into 3 different groups. The first group is the binary. The second group is polyatomic, also known as tertiary. And then the third group will be transition metals. Alright, so as we go through each of these groups, it's important that you make sure that you have your periodic table present, because you need your periodic table to know where the elements are and what the charges are found at on each of those. Okay, so we're going to be talking about binary ionic compounds. And so what does binary mean? Binary means that there are 2 elements that are going to be present. So one of the most common compounds that you've probably seen or heard or even called is sodium chloride. Now remember, make sure you have your periodic tables out so you can understand where the different charges are coming from as I start to talk about them. So in this particular compound, sodium chloride, there are 2 elements. There's sodium, which is Na, and then there's chlorine, represented by chloride. And so now, how do we go about writing a formula from the name? So what we want to do is we want to first understand that the metal sodium is in group 1A and it has a +1 charge. And Cl, which is chlorine, is found in 7A, which has a -1 charge. Now, anytime we write a formula, what we want to do is we want the ratio of metals and nonmetals to be balanced so the charge cancels out and becomes neutral. As we look at sodium as +1 and chlorine as -1, their charges naturally balance out. So what we're left over with is a formula of NaCl. Now, for another example, we'll use sodium phosphide. Alright, now, again, sodium is Na with a +1 charge, and phosphide comes from phosphorus, which is P. Phosphorus is found in group 5A, which has a -3 charge. Now if we look at this, we see that the sodium is +1 and the phosphorus is -3. They're not balanced. And so what we want to do is we want to balance the ratios so that way they cancel each other out. Now, how many sodiums do you think it's going to take to cancel out the -3? Now remember, sodium is +1. If you said 3, you're correct. The question is, why is it 3? Well, if we put a 3 below the sodium here, representing how many sodiums we have, 3 times +1 equals +3. And that +3 will cancel out the -3 to give you a neutral compound. So the formula would be Na3P. So basically, writing the formulas, what we want to do is pay attention to the charges, and we want to balance the charges so that way the ratio of metal to non-metal neutralizes the overall charge. We want to charge a 0 in the end. Now Now, as I sit here and talk to you guys, you know, we do sodium chloride, we've done sodium phosphide. Now the question is, why is it that we name these compounds the way we see it? So the metal is always going to use the element's symbol, all right? So the element name. The nonmetal will also use the element's name, but there's a difference here, is that you're going to use IDE for the ending of the nonmetal. And that will go for pretty much any nonmetal that you come into, especially with a binary compound. Now, let's say we have oxygen, for example. All right, oxygen is O with a -2 charge. So we wouldn't just say oxygen. We would call this oxide. What if we had nitrogen? Well, nitrogen is N with a -3 charge. How would you end this? Would you say nitrogenide? Would you say nitrogide or nitride? Of those three, which one do you think is the most appropriate way of ending it? If you said nitride, you're correct. And so when we end the nonmetals with the IDE, we want to make sure that the way it pronounces it flows easily and smoothly. So let's say you had F, which is fluorine. Fluorine would be fluoride. Sulfur would be sulfide, not sulfuride. So always make sure that when you're naming the nonmetals that you end with an IDE. The metals are always going to be based off their first name. So it's really important that you memorize and you learn the names of the metals and the nonmetals. So we're going to look at just a couple more examples here in this particular part. And we're going to focus on, let's do magnesium and let's do oxide. So magnesium oxide. Write the formula of this compound. So if we look at the periodic table here, magnesium is in group 2, so it's +2, and oxygen in group 6A, so it's -2. Now, just like before, we want to make sure the ratio is constant and it cancels each other out. So naturally, we can see that the magnesium is +2, the oxygen is -2. They're going to cancel, and you're going to be left over with MgO for the formula. Let's look at another one. So let's say now we have magnesium, and let's do phosphorus. Okay, so magnesium is +2, and phosphorus is -3. Now, one thing I want to make a comment about phosphorus is it's really easy to say phosphate because you're used to that from a biology class, or from somewhere else. Most of the time it's ATP or ADP. We hear that quite a bit. But in here we're talking about phosphorus, not phosphate. Totally different compound. As we look at the two charges here, we can see that 2 and 3 is not going to cancel. What we do is we find a common number between the two, which would be 6. So I'm going to put 6 up on top of both of those. How many times will 2 go into 6? 3. How many times will 3 go into 6? 2. That's how you can get your subscripts. So you end up with Mg3P2 for your formula. Now the next question is, what would be the name of this compound? Because we didn't name it. We just started with the elements. Well, Mg is your metal, so that would be magnesium, and P is phosphorus, but we don't want to end with phosphorus. We need to use IDE, so it would be phosphide. So it's important that you understand, why we focus on the charges. The charges are there to help us balance the formulas out, so that way you have a neutral compound in the end. The metal is named using its element name, and the nonmetal, you use the name of the element, but you change the ending to IDE. In the next part, what we're going to be focused on are polyatomic ions. What are polyatomic ions? What is an ion? An ion is something that we defined earlier in this video, and it's a charged substance that's produced either by losing or gaining electrons. Now, polyatomic ions are ions that are composed of two different nonmetals covalently bonded together, and they possess charges, which what creates them an ion. Now, what you're observing is a table of a whole different number of ions that can be found, and I've highlighted some of the major ones that you'll be using in your general chemistry courses. And so the first one is acetate, and acetate has two different formulas. That can be C2H3O2 -1 charge, or CH3CO2 -1 charge. Now, acetate can also be found in acetic acid, just a little FYI. So that's where acetic acid gets its name, is from the polyatomic ion acetate. The second one on the list is ammonium, and ammonium has a formula of NH4 with a +1 charge. Just to note that ammonium is the only cation that's a polyatomic ion. And so all the other polyatomic ions that you're going to work with are negatively charged. Now, carbonate, if you go down a little bit further on the list there, you'll see carbonate has a formula of CO3 -2. And if we go back up to bicarbonate, you'll see that it has CO3 formula, but its charge is -1, and that's because it has one hydrogen attached to it. And so that's where the bi prefix comes from. It's just telling the person that you have one hydrogen. And if you go through this list, and if you find that it says bisulfate, bisulfide, it could, each one of those have only one hydrogen. If we look down the list to cyanide, we see that it also has a formula of Cn-1 charge. Now, the charges are not predictable like the charges are for just, for sodium or calcium or oxygen. These are charges that you're going to have to memorize along with the formula and their name. And so when you start to work with naming the compounds or writing the formulas for the names, it actually is a lot simpler, because you should have at least memorized these formulas and their charges. So we'll just look at an example here where we take, let's do magnesium acetate. All right, so magnesium, looking at the periodic table, is Mg. It has a +2 charge. Now, acetate, looking at the formula, it can be wrote either way. I'm just going to use the CH3 CO2 -1. And what we see right now is that the charges are not balanced out. So what we need to do is make sure we have the right number of acetates to make sure that that charge balances out with the magnesium's +2 charge. In this particular case, you're going to need 2 acetates for every 1 magnesium. Now, you cannot just simply write a 2 as a subscript on the outside of the acetate. What we have to do is we have to write acetate inside of parentheses, and then we'll put a 2 on the outside. So that way, it shows the reader that there are 2 acetates for every 1 magnesium. And so now naming this is like I said earlier, very simple. So let's do one and just name this compound. All right, we know that Na is sodium. What is NO3? If we look back at the list, we find NO3, it is right here. And so the way we would name this is sodium nitrate. Let's do another example. Let's say we have this formula here. What would be the name of that compound? Yes, Ba is barium. But what is OH? OH, if you find, is right here. OH is hydroxide. So this would be barium hydroxide. You do not need any prefixes to tell how many there are. All you have to do is just simply name it using the naming methods that I've talked about already. The metal is given its element name, and then the non-metal, in this case the polyatomic ion, is just named based off of the polyatomic ion. Alright, so again, we're talking about the periodic table. You cannot predict the charges of the polyatomic ions. You're going to have to memorize them. But just, going back from what we said earlier in this video, you can figure out the charges of the different groups. So this is +1, +2, +3, plus or -4, -3, -2, -1. And then we don't worry about the noble gases, as they're not involved in reactions. Alright, so really the best way of getting good at this is to practice. The more you practice this, the better you're going to get at it. And most importantly, you need to make sure you memorize the polyatomic ions and their formulas along with the charges. So we're going to do one more example. Alright, and so we're going to do ammonium oxide. Alright, now going back up here, we're going to see that ammonium has a formula of NH4 with a +1 charge. Oxide is oxygen with a -2 charge. We can see that the charges are not balanced. The question is, how many ammoniums are you going to need to balance out the charge on the oxygen? Since ammonium is only +1 and oxygen is -2, you're going to need 2 ammoniums for every 1 oxygen. So we're going to put the ammonium ion into the parentheses with a subscript of 2, and then we'll have oxygen on the outside. And so that would be the formula for ammonium oxide. So I hope this little video helped you out with polyatomic ions. And next, what we're going to do is we are going to cover transition metals. Okay, so we're going to be talking about transition metals now. And so first thing we want to do is we want to understand where the transition metals are found on the periodic table. So the transition metals are found here in the B group. So these are transition metals. What exactly is a transition metal? Transition metals are not like your typical A group elements. They are going to vary in charge in oxidation states. So we have to take that into consideration whenever we're naming them or writing their formulas. So the majority of these have more than one oxidation state that are found within the B group. And so this group here that we're looking at is called the B group. there are several elements that we are going to focus on, and I'm going to circle those now. These are elements that you typically are going to see or work with in the lab, and their charges are going to vary. And so there's two over here. Yes, I'm going outside of the transition metals, but these two, SN and PB, also vary in their oxidation state. So let's start up with chromium, for example. So chromium can have a charge of +3 or +6, and those are the oxidation states that you're going to see them in more commonly. Iron has an oxidation state of +2 or +3. Copper has an oxidation state of +1 or +2. Silver is unique in the fact that it only has +1 oxidation state. Gold, you rarely will work with gold, but it's good to see the pattern here. Gold is +1 or +3. Now, if you pay attention to this group, these are all found in 1B. And if you notice that each of their charges start off with +1. And so copper can have +2 and gold can have +3, where silver only has one oxidation state. Zinc is another element that doesn't vary. Zinc is +2, and so if you notice, it's in 2B, so that just makes it a little bit easier to remember copper, zinc, silver, just using the group numbers that are found above. When we get over to tin and lead, tin is +2 or +4, and then lead is also +2 or +4. Now, a detail that you'll want to make sure that you pay attention to, this is a really important detail, is that when you name a compound that possesses a transition metal, you should always use a Roman numeral. The only exceptions are silver and zinc, where they only have one charge oxidation state and they don't require a Roman numeral. So let's say we have Fe2O3 and we want to name this compound. The first thing we want to do is we want to figure out the charge on the iron, and you can't just simply crisscross to figure that out. What we're going to do is we're going to look at the charge of oxygen, and we're going to figure out what the charge on iron is. The charge on oxygen is -2. Now, we know this molecule, this compound, is neutral, so we set it equal to 0. So how many oxygens are there? There are 3 oxygens. Each oxygen has a -2 charge. So 3 times -2 gives me -6. What we want to do is try to solve for what x is. In this particular case, x is going to be +6. And if we look at the subscript, there are 2 irons. 6 divided by 2 gives me +3. So the charge on the iron in this case is +3, and that's because that +6 is divided into the 2 irons. So whenever you're naming this, you're going to use iron 3 oxide. So again, this 3 tells you the charge of the iron in this example. And you have to do this in every example that possesses a transition metal. So it's really important that whenever you're naming compounds that you look on the periodic table at the location of the element. If it's a transition metal, make sure you use the Roman numerals. So let's say we have copper 2 hydroxide as another example. Now what I want to do here is I want to write the formula from its name. Now copper 2, okay, that tells me there that I have copper +2. And we just learned earlier that hydroxide is OH with a -1 charge. Now, same concept, you have to go about, figuring out how many hydroxides you need for every 1 copper, because the charges don't balance out. In this particular case, that's easy. You need 2 hydroxides for every 1 copper to balance it out. So the formula would be CuOH2, and do not forget the parentheses. Now let's look at a couple examples here. So let's say we have CrO3 versus Cr2O3. Now earlier I said you don't want to crisscross. One of the things that people tend to do is they want to crisscross. If you crisscrossed both of these examples and you see that both of them have 3 oxygens, you'd be telling me that the chromium up on top and the chromium up on the bottom both have a +3 charge, which is not true. Alright, so what we need to do is we need to figure out what the charge on each chromium are just by going through a simple calculation. Now we know the charge on the oxygens are -2, and so since there's 3, that's a total of -6. Now we set this equal to 0 like we did earlier, and we're trying to solve for x in each case. Now the top one, well, 6 minus 6 equals 0. Alright, so 6 in this case is your x. Now how many chromiums are there in this compound? There's only 1 chromium. So that means that this chromium is +6. Now looking at the bottom chromium, alright, we can also see that that's going to be 6. Now the difference is that there's 2 chromiums in this formula. So 6 divided by 2 gives me +3. So the name for the top one would be chromium 6 oxide, and the one on the bottom would be chromium 3 oxide. So going back to what we said earlier, you want to make sure that you figure out the charge by going through the math, not just crisscrossing, because you can see there is a difference. The chromium on top was 6 and the chromium on the bottom was 3. If we went through the crisscross method, we would have said both are 3, and that's not correct. And that's a good way to get a question wrong if you're ever in that type of situation. So let's look at one more example here. So let's say we have lead 4 nitrate. Alright, so what's the charge on the lead? Right, it's +4. And then nitrate, looking back at the formulas, is NO3 minus 1. How many nitrates does it take to balance out the lead's +4 charge? 4. And so the formula would be Pb NO3 4. Alright, so any questions on this? If you have any questions, you can always leave a comment below and I'll get back with you. And that's it for ionic compounds. Thanks for listening.